In this last lecture of the semester, we will focus on the applications of the local components of very differential encoding theory. Particularly, we want to understand the dual structure of, by the dual of we mean the dual of a linear code, dual structure of the algebraic geometric codes, again in terms of another algebraic geometric codes. So for this purpose, let me remind quickly the first construction we consider algebraic geometric codes from a function field f of genus G. And in this construction, for the length of the code, we need pairwise distinct and pairwise distinct rational places. This also tells us the residue class, their residue class fields indeed the constant field in this case. And we consider another divisor, G, which has disjoint support from the support of D. And indeed, by evaluating the functions in the Riemann space of L of G, it is given distinct places. We have seen that evaluation D is a linear code, FQ linear map with kernel L of G minus D. And by the first isomorphism theorem, we were able to estimate its dimension and moreover the parameters. So by the notation, let me simply write, we denote such a structure with CL of DG. And in general, the story, we can estimate also its parameters in terms of, by using the Riemann theorem. And now we are indeed main goal in this lecture will be to represent the dual of this code. By the dual, we mean the orthogonal complement, and this is determined by the standard inner product on the n-dimensional vector space over FQ. And we will see that indeed it can be viewed in terms of another evaluation map. But in this case, we evaluate the functions of the Riemann space in the Riemann space of the divisor H. Here H will be determined in an appropriate choice. So indeed, we will see that for some spatial canonical divisor, we can write it in this form. So in general, we want to investigate what is this weil differential and how we can understand it in terms of the local components. But the first step for this equality will be to introduce another algebraic geometric code. In this case, instead of evaluating functions, we consider the local components of a weil differential from the weil differential space of the divisor G minus D. Particularly, we look at their local components of 1. This is P1, this is Pn. Again, here PI's denote the pairwise distinct rational places. And indeed, we can also see that this is bigger than G minus D. So for this purpose, for this construction, this is also our another claim in this lecture, in that we will see that this code, indeed, the dual of the AG code, which is described in terms of the evaluations. And for this setting, let me fix the notation. As for a divisor A, for the Weil differential space of a divisor, in general, we mean a zero differential or its divisor is bigger than or equal to A, and we know that this is a finite dimensional vector space. And moreover, we also know its dimension as index of specialty. So that means in this setting, the image of rho D, that means rho D will be FQ linear, and we can understand its kernel, and the image of rho D gives us this structure. So that means we will be more or less estimate the dimension in terms of the index of specialty. And for a Weil differential, in general, it will be non-zero in the proofs. And for a given place P, we treat the local component of this Weil differential at P as a map from the function field F to the constant field FQ. And with this setting, we can also see that, obviously see that this rho D is FQ linear by the linearity, FQ linearity of the local components, and moreover, this definition makes sense. Obviously, the images are going to be elements in the finite field. In a more precise way, we denote the image of this map by C omega of D and G, which contains the intuples, and these tuples are determined by the local components of a Weil differential omega of 1. And this is also called an algebraic geometry code. And the FQ linearity comes from the linearity of rho D, and indeed, obviously, this is the n tuple, so the length is, and moreover, this is a subspace in FQ to the n. So that means if a finite dimensional vector space, obviously this has a linear code structure. And the second question is obviously, if we have a FQ linear map, what's its kernel? Because, and then by force isomorphism theorem, we can give the exact dimension. And to understand its kernel, we want to look at the Weil differentials, which gives us 0 at each component. And so that means we need to understand when do we have such an equality. And in order to see that, first, this is not going to be so trivial. Our first claim will be for a given rational place P and a Weil differential omega, which might have pole at P of order at most 1, then its local component at P of 1 is equal to 0 if and only if indeed it has no poles at P. And in order to prove this equivalence, this characterization, we need to use proposition 1.7.3, which let me recall its definition. Let me recall its statement, which tells us indeed we can decide the poles or zeros of this weil differential at given place P actually it's order, pole order or zero order, by looking at all functions that might have zeros and poles at most this order or at least order R, and its images under the local component of the weil differential at P is going to be 0. And we may even reduce this statement. So that means for any integer s, Vp of s is bigger than or equal to s if and only if Vp of x is 0 for all functions that have poles predescribed poles or zeros at this given place P of order at least or at most S. And in order to prove our claim, so in order to be able to give this characterization, we work with this statement, which is reduced from the proposition 173. And in particular, for the sufficient condition, if we suppose that this weil differential has no poles at place P, by using this characterization, indeed we can see that Vp of x 0 for all functions which has no poles at P. So this is also true if it is true for all x. So that means it also holds for particularly for the function constant function 1. That means we have Vp of 1 is 0 because its valuation is bigger than or equal to 0. And in order to see the necessary condition, conversely, let me suppose that Vp of 1 is 0. And similarly, we want to use this statement. And in particular, let me consider a function which has no poles at this given place P. And in order to see, and in this case, our claim will be Vp of x is 0. And in order to see this claim, let me first observe that since Vp of x is bigger than or equal to 0, we can see that x is indeed an element in the discrete valuation ring OP. And since the degree P is 1, so that means we are in the residue class field, and this is isomorphic to K. We can note that any function here can be written as a plus y. Here a is from fq. This comes from the rationality of the place, and with function whose valuation at p is strictly bigger than 0 or bigger than or equal to 1. And thanks to this representation, if we look at Vp of x, omega p of x, indeed, it's enough to check the omega p, the local component of omega at p of the function a plus y, and we know that this local component of Weil differential is fq linear. We can write it as Vp of y. And in this equality, let me note that this quantity is going to be 0, because by the assumption, we know that Vp of omega is bigger than or equal to 1, and Vp of y is bigger than or equal to 1. And by this characterization, which we consider in the statement star, we know that the local component of the function y is going to be 0. And for the Vp, and yes, this is also by the assumption, we know that this is equal to 0, and this shows us Vp of x is 0. And indeed, this completes the proof of the claim. Briefly, in general, in particular setting, if you consider Weil differential from g minus d, so that means omega, the divisor of the omega is bigger than or equal to g minus d, so that means Vpi omega is bigger than or equal to Vp of g, but they have a disjoint support, it's going to be 0 minus Vpi of d. This is obviously minus 1. So that means such a Weil differential, we are in this case. So that means this case satisfies the conditions of our claim. And thanks to our claim, we have seen that this local components of 1 is 0 if and only if omega has an opposite at p. And thanks to this characterization, indeed, we can rewrite the kernel of rho d in terms of discrete valuation maps. Which contains the Weil differentials from the Weil differential space of the divisor g minus d, such that omega pi of 1 is 0 for all places in support of d. Or in other words, thanks to what we have seen in our claim, we know that these are indeed the Weil differentials, which has no pose at this given places p. And since omega is bigger than or equal to G minus D, but it has no poles this in the support, any places in support of D, indeed we can see that these are the weil differentials, which is either 0 or this is bigger than or equal to G. And indeed, again, by the characterization of the space of the weil differentials of a divisor, we can see that this kernel is the space of weil differentials of the divisor G. And by the first isomorphism theorem, indeed, image of rho D can be seen as the quotient space of these two weil differential spaces. And in particular, we can see the dimension of this AG code can be computed in terms of the difference of the index of specialties of the divisors G minus D and the G.